So it's my pleasure to invite the first speaker in this season, Bruno Bauwens, our international specialist, and the talk named, what is the correct name of the talk?
Well, I will speak about information distance, and there is a definition from algorithmic probability, so I will use excuse to speak about Solomonoff induction because I think it's interesting. Okay, sorry, I forgot what is the title. Okay. It's not important.
Algorithmic probability and the information distance. So please, you have 1 hour and 20 minutes with the questions.
Okay. So main goal is to clarify some subtle issues in the definition of algorithmic information distance. But first, let us think what is philosophy. So imagine an engineer, he has two discrete objects. He wants to understand how different are these objects. He wants to measure how much differs the information in both objects. For example, he has two pictures, and he wants to say, does this picture contain different information? And so he can say a picture is basically a vector with RGB values. And so he can say, first idea, let's use, how it's called, Euclidean distance. Euclidean distance, because they're vectors. And so, but maybe this definition is not a good idea. For example, if you have picture, an inverted picture, one could say they contain the same information, but Euclidean distance of the values will be maximally different. So can we make more clever measure that incorporates such small transform? And so, we can add some transformation, allow for color remapping, and increase and apply small punishment. Okay, but then what about if one image is a little bit translated? So we can also add about translations. And then what about rotations? And what if the same picture is taken from different angle? All these transformations, they reveal the same information. And so it becomes harder and harder to make intelligent distances that can be used for... So the dream is to make one distance that's really intelligent and can be used in many different applications. And so it's not a practical dream, it's a mathematical dream. However, there was a time 20 years ago where this dream gave a very important idea to real engineers. So answer from mathematicians is, let's look to a symmetrized version of conditional Kolmogorov complexity. I will explain everything, don't worry, for those who don't know. So the symmetrized version could be approximated with real-life compressors. And so they could, 20 years ago, solve with very fast algorithm, make in many different disciplines with a single, very small algorithm. They could have breakthroughs in many different fields of expertise. And so one important field was bioinformatics. So in 2003 was beginning of internet, so researchers put gene sequences on the internet, they could be downloaded, and there was GZIP compressors applied that approximate distance. They were given to hierarchical clustering algorithms, and they could recover evolution tree of different species. So there was hierarchical cluster algorithm that puts objects in leaves of tree. And this tree was what biologists agreed on is most likely evolution. But they used mitochondrial DNA. Okay, it's technical thing. It's just a bit shorter DNA sequences on part of the cells. Yes, and there were also controversial evolutionary trees where biologists needed a long discussion before reaching agreement. And this algorithm also produced the same tree for which agreement was reached after some time. Another example is Russian books. And this I did myself, this experiment. So there are 25 Russian books from Bulgakov, Gogol, Dostoevsky, Turgenevskaya. And so I run a standard hierarchical cluster algorithm, and it just computes for minutes and it produces a very reasonable classification. So I can show in the camera and to the people. So if people are interested, so I leave it here.
And here, what is the distance?
Distance is normalized algorithmic information distance. So there is some normalization. I will not speak about it. And it was computed with gzip compressor, which is a very fast compressor. So now it runs in minutes. So with language model and all this advanced thing, it would be.
Question. Once some books of Google are more close to book to Dostoevsky than to the other book of Google.
Yes, so
What, how to explain this? Your picture shows that the cluster of books books of Google, some are very closer.
Close, yeah, they are in the same color. Yeah.
How to explain it?
Well, first, the program assigns colors to these things, and why this happens and how it happens, it's not in the output. It's just some plotting program in some stage assigned color. I have no clue how it works. And so according to this, it's not nowhere documented. And so I didn't read the source code. So don't worry about the colors. But indeed, they're quite close. You should ask a linguist or why.
So what is the procedure? You compress the books or you...
No. So there is. So all these books are distributed on a single website distributor. So they're more or less the same format. And so I use these files, took random pieces from the books, then computed these distances, and then gave to what's called hierarchical cluster algorithm. And then it recovered. But it's just reproducing Vitani's experiment from 2003. So, but with modern cluster algorithm. But experiments are the same, except there is one mistake. But somebody told me who read these books that is a plausible mistake. I think Gogol or Dostoevsky there has a special book in old style, and it is. Okay, it doesn't matter, it's just example. Let's speak about mathematics. Yes. So let us first repeat what is Kolmogorov complexity. And I'm sorry, many people already know, but also some people do not know. And I will start to write here. So what we have is a Turing machine. And it's a device that maps programs to outputs of programs. And so it maps strings to strings. And there are three interpretations. So either we view it as decompressor, we give it .zip file, for example, and it decompresses to original file. So second interpretation is programming language. So U is compiler or interpreter. We give a program, it expands to the captured output of program. And so third is formal definition is Turing machine. So this device, it moves over the tape cells and then manipulates cell where the computation head is located. And so we can view it as a device mapping strings to strings again. Okay, and now we can say what is Kolmogorov complexity according to the device. So it is equal to minimal length of a program that outputs X. Yes. So there is definition. So now the question is, this definition depends on the device. What device should we use? And so it's a good idea to use universal Turing machine. So I will have many definitions, so I will make my life easy, not use optimal machine like many Russian people do. So what does it mean? So U is universal if it can simulate any other machine, if you prepend a description of the other machine to the program. So U is universal if for every Turing machine V, so there exists a string, a description D, so D is a string, so that for every program P, the result of concatenation D and P is equal to V of P. So it's definition. It means that, so if you give U a description D of the machine V, then it simulates the machine V on program P. So it's clear, right? And so, so there exists a universal Turing machine. And so it's easy, especially if you think about Turing complete programming language. And so corollary of this is that if U is universal, then for every Turing machine V, the Kolmogorov complexity is better, but you may lose at most a constant. And so for every Turing machine V, there exists some constant depending on V for every X. Kolmogorov complexity of U is smaller than Kolmogorov complexity of V, according to V plus this constant CV. And so this is, it means that if we take two universal Turing machines, Kolmogorov complexity function is equal up to some constant. And so for applications, we need to believe two things. First, that our objects are quite complex, so that this constant doesn't matter. But also in application, we need to compute these values. And so we need a real-life compressor that somehow can capture enough of the structure in the string. Okay, so yes. Let us make some observations. So if we have universal machine, then complexity of X is bounded by length of X plus O of 1. So how can we prove this? So how do we prove every inequality with Kolmogorov complexity? We will consider special machine and then use corollary. So here we consider the machine that maps VP, just the identity machine. It maps the program to itself, and so we understand that Kolmogorov complexity of any string X is exactly the length of X on this machine V. And so when we move to universal machine, we just add O of 1 because of corollary. So it's very logical. And so this is a trivial upper bound, and it's pretty good upper bound. There are only few strings that have small Kolmogorov complexity. So let us make quantitative statement. So number of complexity strings, number of strings complexity smaller than k. It is bounded by number of programs smaller than k, which is which is this geometric sequence. 0 length programs, 1 length, 2 length, and so on. And so it is smaller than 2 to the power k. So random string of length n will have complexity n smaller than n minus d, only with 2 to the minus d program. Okay, so people are getting tired. It looks like, oh, this is already known. So yeah, so I need to guess. Either I go
ask
to
a question. When I was a student, I was on the lecture of Kolmogorov himself. And as far as I remember, he said that either the program is finite for any string, or it's of the order of the same as the message minus something multiplied by log n. Is it correct what I'm saying?
I didn't understand.
Okay. Maybe I'm wrong, but my working memory is the statement of Kolmogorov was many years ago, 30 years ago, 40 years ago, was like this, that either there is a final program that produces strings of any length, or the length of the program is comparable to the length of the message up to some logarithmic term. Is it correct? Well, maybe it's much improved from the time, I don't know.
Okay, what you say remind me a little bit about prefix complexity.
Okay, it's different.
Where this is not true, and you need some logarithmic term. And I still didn't get the question, but maybe when we change the complexity, you will understand.
In many theorems about plane complexity, additive logarithmic term also appears.
Yeah, it's about complexity of pair or some.
Yeah.
Okay, yeah. Yes. So for a random string with high complexity, this bound is good. But there are very structured strings. So for example, if we have n zeros, then complexity is close to 0. It's logarithmic. Maybe that's also. So if we complexity of n zeros is smaller than log n plus O of 1. And so again, we need to think about the machine V. And what V does, it gets a program, interprets it as a number in binary, and then print this amount of zeros. So this is true. Without O of 1 for such a machine V, then again by the corollary, it's for every universal machine, this is true. So what I will do is, I will fix such a universal machine and then drop the index. So it is common because it's kind of invariant notion. For two universal machines, complexity functions are equal up to O of 1. Okay. So this is for complexity. We will also need to speak about conditional complexity. So information distance is variant of conditional complexity. So here we use the machine that maps pairs of strings, so a program and some auxiliary input to a new string. And so complex, so the information in X that's not in Y is defined by minimal length that maps Y to X. So definition of universality, we just input argument Y here. And so conditional complexity is minimal up to constant. Okay, and so everything's still valid for conditional complexity. And so there are some easy properties. For example, conditional complexity is bounded by unconditional complexity, because program can always ignore auxiliary input. Complexity of X given X is bounded by constant, because we can have a silly program that just copies the auxiliary input to the out. Okay, so there are some signals. I should try to go faster. Yes. So let us now tell what is information distance. It's minimal length of so information distance of two strings is minimal length of a program that maps the first to the second as well as the second to the first. So let me write definition. So on the machine U is minimal length of P, and the program is bidirectional. So UP of X needs to be equal to Y, and UPY must be equal to X. Okay, so now let us try to understand a little bit what is this meant. So again, if we take a universal U, then our function is defined up to a constant. So I will then just fix universal U and drop prefix. Yes?
So it wouldn't be difficult to explain why the triangle inequality for the distance holds.
Okay, it's a good question. I will do it in a second. Let's first make some simple observations. First observation is that D must be larger than conditional complexity. Just because there is a second. So here is the requirement. Sorry, here is a requirement for conditional complexity, but now there is additional requirement, so it becomes larger. And so we also have that it's bigger than Cy plus Cy given X plus O of 1. So why this is true? Okay, I'm doing something incorrect here. I will say something incorrect now. So, but then there's a question to reveal all my mistakes to you. So we need a program that maps X to Y and Y to X. So let's concatenate a program that maps Y to X and X to Y. And so concatenation is the new program, and that proves this inequality. So now your job is to disagree with me and say where are there two mistakes in this reasoning.
Well, we need to also add the interpreter that interprets two programs. that parses two, the concatenation of programs as two separate programs.
Yeah, indeed.
Not just discussing
Yes,
one. So
exactly.
it's one, and there is another of one, right?
Yeah, yeah. So let me first deal with the problem you addressed. So just let's repeat. So we concatenate two programs, but then our machine U will get a concatenation. He needs to somehow split the two programs, so then he can evaluate one of them.
And
So-
then it's not clear how we split the programs.
Yeah,
because-
yeah, yeah. So I need to give it, I need the third thing. I will put a number in prefix binary
but it's
in the
not-
front so that it can read this number. And then it knows it has to start reading after this number so that to split it. So we need a little bit more. So we need 2 log cx of y plus O of 1. y2, because we need to put it in prefix-free form. If we put this number in binary, then again we don't know where to split.
Do you understand right that D is symmetric, so you put maximum cxy and cyx, yes, to the left hand side.
Yeah, yeah, yeah.
Or maximum between two.
Yeah, so that's true for cxy, but also for cyx, that's also for the maximum. Yeah. Okay, so now I fixed the first problem. So our combined program has 3 parts, but there is I still cheated with this proof. So where is the second problem?
How do we know what's X and what is Y?
And exactly. So we need to add hash code to distinguish them. And so in the worst case, you need like a 4, something like, but with 4 logarithm. Well, no, that's not true. So hash code will be 2 times, for example, log x. Well, it's a good idea to take the maximum of the length. So hash code is logarithmic. The hash codes I know. Okay. Yes. So now it's correct. But now there is. So let's do more examples. If length of x equals length of y, then dxy is smaller than length of x plus O of 1. So how can we prove that one? So we need a program of length x that maps x to y and vice versa. What can be this program? Okay, so it's...
Oh, the length of x and y are equal.
Yeah. Okay, so it's easy. So command.
Just store both x and y.
Yeah?
You cannot just store the x and y.
So you take XOR, bitwise XOR. So you check, so you write x, and then you say y, and then you write down all the bits. So you write the when the bits are different, and a 0 when the bits are equal. And so if you know this difference, you can just add it to x or add it to y to get the other one. So bitwise XOR. Okay, so now we did some fun exercises. And this is enough for, your question about triangle inequality. So let's, more general, axioms of metric. So dxx smaller than, is it bounded by a constant? Of course. So, oops, O of 1. Second axiom is symmetry, which is by definition. Okay, my writing is terrible, just symmetry. Third rule is triangle inequality. So it's only approximately true, triangle inequality. So we have that dxy plus dyz is bigger than dxz after we subtract some logarithmic term. I think 2, something like this. Doesn't matter.
So one.
Yeah. And so the problems are very simple, and there is a counterexample. So you can prove counterexample where all the lengths of x, y, z are equal, and where this is log n. And so okay. Let me write. Okay, I will not discuss the counterexample. So it would be natural to require triangle inequality with O(1) precision, since everything is defined with O(1) precision. Okay, so yes, for plane complexity it doesn't work, but it's also no specialist uses this plane distance. I'm using now for the sake of the seminar because definition is easy and we can prove something nice with it. So they will use prefix variant where U is prefix machine. But then we will have other trouble. But this is for the second part of the talk. Actually, sorry, last part of the talk. Okay, so let's now prove something. The theorem says that the d of x is equal to maximum of conditional complexities x given y and y given x. So theorem by Lee and Vitani in 1992. And the abstract, so I Googled something I forgot and found this paper from 6 years before the reference in the abstract of this talk and all my papers. So I didn't know till yesterday that it was already 1992. So everyone cites paper from 1998 with 5 authors, with Vitani, Zurek, Gach. Okay, so let me write down the theorem. Oh, let's reuse a little bit. So theorem says that this is equal to the maximum of these two things plus O(1). Yes. So now we will prove this equality.
So it's actually two inequalities, and it's
yeah.
then maximum plus O(1) and less than. So one inequality already observed.
Yeah, indeed. So we already know that it's bigger. So this one is okay. And so what we need to prove is that it's smaller. So this is the theorem by Lee and Vitani at 1992. Okay. And so to prove theorem, I will consider game on a graph. And this, so let us say what is game. So it's edge coloring game. So we have a graph. And so we have a bunch of nodes. Initially there are no edges. And then the opponent, it will, so game has two parameters. There is a maximum on the degree of the graph and a number of nodes, colors. So let's call it, sorry, D is already in use. Let's, okay, D prime is degree of the graph, and K is number of colors. And so opponent enumerates edges like this, and such that the graph that appears has degree at most D prime. And each time an edge is enumerated, we have to assign a color to the edge. The rule is that if two edges are incident on the same node, they should have different colors. So that's the game. And the little lemma says that if number of colors is equal to 2 times the max degree minus 1, then just greedy strategy works. So why is it true?
So works means that which player wants.
So the player who colors can always do it. So the player who colors will win.
One player.
Yeah. One player
chooses
edges, other player chooses colors. Yes. And so 2d prime minus 1 is enough for player who colors to win by greedy strategy. So why is it true? Well, when a new graph appears, yeah, so let us look. Imagine that he enumerates now a new edge. So the moment he enumerates this new edge, we know that right before this edge arrives, both nodes have at most d prime minus 1 colors assigned to them. So both the left and both the right node have d minus 1 colors assigned to them. And we need to color this edge with a color so that no node has two edges with the same color. So that means at most 2 times this many colors can be unavailable. But we have 2d prime minus 1 colors available, so we have always 1 color left.
Do you claim that this number is minimal?
No.
I thought that
For our theory, we don't care about constant factor here. So for offline coloring, if you get the graph at 1, there exists some theorem that says d prime plus 1 colors should be enough. If I remember, actually, you told, I think, yeah. Some student told me that there exists some theorem in graph theory for edge coloring. But note, we need greedy strategy, and we don't care about factor here, because colors will be programs very soon. And we don't care about adding a constant to the program. So we can increase the program always by constant length, so we can have a multiplicator on the colors. Okay, so this is first step. We understand about greedy coloring and this game. Second, what we do is we need a graph that corresponds to our problem. So note that we now are trying to prove this inequality. And so our plan will be to prove something like this. So we construct special V that satisfy this. And let us look to the constraints that we have here. Let's write them in a graph. So let's define a graph GK. I will define it here. GK. So we say that an edge xy is in GK if and only if Cx given y is smaller than k and Cy given x is smaller than k. So nodes will be all strings, and the edges of the graph will be all pairs xy that satisfy this condition. So that's our graph GK. Okay. So now if we have a graph, so this is a graph we can enumerate. So we can check many programs. We evaluate programs for increasing runtime, and when we discover that this and this is true, then we can make the list of edges that we have to add. Okay, now it's time to say how our machine V works. So it will receive a color and a string Z. Machine V will start to enumerate this graph, and each time an edge comes, it is immediately colored. And it keeps doing this until it sees that node Z receives an edge with color R. And then it will output the neighbor, the corresponding neighbor of this edge with color R. And so if it sees that edge Z tilde has color R, then it outputs Z tilde. So should I write it or repeat it? So some people say it's clear.
Can you please repeat why such an edge exists?
Well, actually, I didn't say what is K. So let's write it. So enumerate G length of R minus 1. So it will set K equal to R length of R minus 1 and start to enumerate edges. So it searches for pairs that have small conditional complexities. If it finds such a pair, it will assign a color. And so it will enumerate this plus color with 2 to the power r bit strings. So bit strings of length r. So colors will be strings of the same length as r. So note that here, max degree, I didn't forget to say. So what's the max degree of graph gk? It will be 2 to the power k. So max degree, actually strictly smaller than 2 to the power k. So it means that we can color this graph because I dropped the k by 1. And so there are enough colors to color this. So this is the first step. Enumerate the graph color, and I've chosen the parameters so we have enough colors. We will have more than this number of colors. And d prime is equal, so I choose d prime equal to this.
Sorry, how many colors we have?
So length 2 to the power length of r. Length of r. But k is chosen a little bit smaller. So that we have enough colors compared to the degree. And then the second step, if z tilde gets color r, output z tilde. I don't know if it's reasonable. My writing is, so I read it again. If z tilde appears with color r.
Is it an integer or a string?
So this is the input. It's a string.
It's a string.
And we view it as a color.
Oh, I see. Right, left.
Yeah. So this is machine V, and machine V achieves precisely what is written here. So if max complexity is equal to k minus 1, then there will, in the graph, we will get a color assigned of length k. That's right. Yeah. A color of length k will appear, and so bidirectional mapping will happen. And so here is magical theorem by Vitani.
Is it an original proof?
It's quite close to original proof. Yeah.
They used a game of some sort of this.
I don't remember, but it's quite close. So whether
Yeah,
they use the word game, I don't remember.
I'm interested who invented the idea of such games.
Yeah.
Of course, it can be reformulated in terms without any games at all.
Yeah. It's written
clear.
without the word game, but
Yeah,
it's
yeah.
incredibly close. I mean, there is not many ways to write this proof. If I remember correctly. Anyway, if there was a major change, I would have noticed many times ago and then remembered about it. Okay, so now we have proven, let's go back to our theorem. We have proven that is equal up to O of 1 constant if we go back to universal machine. Okay, and this is important for applications. Why? Because making a compressor that produces a bidirectional description, it's really hard. However, one directional description is easier. So there are a few papers that try to do this, but not many. But what is easy is just compressing one string, because typical compressor does. And so there is a last step for applications. So conditional complexity is approximated by the chain rule, C minus X. So there is a theorem, conditional complexity equals this difference up to logarithmic terms. And this is now easy, so you can just in gzip put a concatenation and just put one of the strings and then compute everything. Okay, so now we finished first part of the talk. Let me check about time. So I've spoken 40 minutes. But the last part is smaller. But there is a little trouble, so I will fail to do everything. Okay.
You can use a surfboard.
Yeah. But we won't need it for a long time anymore. So I will. So we will stop speaking about this. And now I will explain very different story about Solomonoff induction. And there are very few proofs now. So Solomonoff, he invented this theory in 1956 till 1960. It was beginning of artificial intelligence, and his teacher was a philosopher called Rudolf Carnap. And he wanted to understand, he said that we need philosophy about what is probability, how to use it, and so on. But he also thought about philosophy, what is science, how should scientists operate, and he believed that science and probability should have precisely the same philosophy. And so Solomonoff learned about this, and then he went to Dartmouth School on Artificial Intelligence. It's very famous summer research moment where many professors came who were very young, but half of them received Turing Award later. So there was McCarthy, Minsky, Claude Shannon, and so the goal was to think how machines can be thinking. And so Solomonoff said we should have 3 times the same philosophy. So what could be, so how machine learns, how human do science, and how to assign probability. And so he wanted a very general model, and so he thinks about a black box and it produces bits. So in finite or infinite sequence of bits. And the question is, if you see a few bits, how can you predict the next bit? So he says, let's agree on something that, imagine that for some mystical reason, all philosophers can agree on a semi-measure. Then we can maximize probability according to semi-measure, and we can make a prediction for the next bit. We can maybe even use this probability to assign conditional semi-measure. So what could be this probability measure? So what could be the semi-measure? But now I have to say what I mean with semi-measure. So I need a definition. And so P is a mapping from strings to a real interval 0, 1. And we say that it's a semi-measure. So if P of x0 plus P of x1 is at most P of x. And so this for every string x. So, and also empty string P of empty should be bounded by 1. And so here it's important we use inequalities. We will never need equalities, but equalities will create big trouble later. So, okay, imagine that we agree on semi-measure P. So we can now think what is prediction of bit n plus 1 after we see x1 and other bits. So, as I already said, we can maximize our semi-measure. So we can look to argmax of here if we append an extra bit. So it's very simple strategy. So now we can bound the number of mistakes using the measure P if we follow this strategy. So number of mistakes is bounded by logarithm 1 over Px xn. So number of mistakes in the first n predictions is bounded by this logarithm, binary logarithm, as usual in computer science. So why is this true? It's my question for you. So there is very little information on the board, only 2 rules. So you have very little to think about, so why is it true?
Do you mean an expectation or
No,
absolute?
worst case number of mistakes for every
Worst
string
case.
x.
It means that we begin with an empty string,
Yeah,
and
yeah,
then we produce.
yeah, yeah. At any moment for every n and for all the x's, this is always true. Yeah, we start with empty string and predict x1, then we get x1 and we predict x2 and so, yeah.
Okay,
Yeah.
okay, yeah. So let's just bound with all this equality. So the, with the probability of making at most k mistakes, this means that we produce. Can bound it by producing first n minus k bits right, and then every bit, everything.
Yeah, so
else
it's a
wrong.
very short proof. So we should think what happens when we make a mistake. So let's look to our basic only inequality. What happens when we make a mistake? So so we know that if we predict 1 and 1 is wrong, it means that our string continues with 0. And this is smaller. So that means less than half of the probability in px remains in our new string after we append the next bit. So at each mistake, the new probability decreases by at least 1/2. And so that's why we get this logarithm here.
What you think about the law of Bauwens in the sense that mean number of right answers cannot be smaller than information. If you take expectations, suppose it's a random string, then it would be natural to say that mean number of correct answers is bounded by the information.
Yeah,
Which
yeah,
would be expectation of this expression.
Yeah. So expected number of mistakes is much lower. This is worst number of mistakes.
Wait, it's mistakes.
I mean, low bound. You cannot do better than you.
No, it's upper bound.
And but low bound also should.
Yeah. Lower bound, okay, but then we need some probabilities. Nowhere do we have probabilities. We just have this function here. So there is no random variable in the analysis. So just say for every choice of n and for and the n bits, this is true. That during the first n predictions we make this many mistakes.
The number of mistakes here is not the same as Hamming distance between the most probable string of length n and the produced string and the expected string.
Yeah. So no
the
random
same.
variables. There are no random variables. There is just a statement.
I mean that there is if there is a string that is produced by the machine, if we run it with the starting
No,
string
we
as-
don't have machine. Nothing. There is just a semi-measure and the promise.
Actually, it's an algebraic statement.
Yeah.
Each time you make a mistake, probability diminishes at least 2 times.
Is it okay? Let me ask a question one way. So it's the number of mistakes. It means on each step, we just look at this very step, and see if we produce the correct bit according to the.
According to this strategy.
According to this strategy, but if we already.
Okay, this is just a little game. I don't want to spend time on this. So what I want, why do I explain this? So if you want good predictions, we want to have a measure that is as large as possible. That's the whole reason. Okay, so now we need a notion of domination. So let us say, I will write less than star for saying that Q is better than P. And so very naive definition would be to say that for all x, P of x is smaller than Q of x. But then, so our goal is to define a largest measure in some very big set of measures. And then let's try to agree on the largest measure to define Solomonoff prediction. That's our plan. So, okay, so this is too strict. So let us weaken the definition, because otherwise on the 0 and the 1 string you can always be smaller. As soon as you have two measures, you have a problem. So let's then say we allow a constant factor in our requirement. Constant factor means in our little toy statement, a constant number of mistakes. And so if we have two people doing science, we agree on a constant number of wrong predictions but we don't agree in some unbounded number of different predictions. Okay, and so if we want a biggest measure according to this order, then when we consider all measures, it will again be impossible. There's just too many measures. So the next idea is, let's look to computable measures. So do we have a biggest computable measure according to this order? And so answer is negative. And so if I have a measure P, or if I have a measure Q, doesn't matter. So here is Q empty, and then here we have Q1, and here we have Q0, and so on. Q0, 0, 0, 1, and so on. Then we can create a new measure that's way bigger, and if Q is computable, our new measure is also bigger. And it will be a measure that concentrates everything on one sequence. And this sequence will be the sequence where we choose every child according to the lowest value of the measure. So we can make a path where Q decreases geometrically, and then create a new computable measure that assigns 1 precisely along this path. And so the ratio is unbounded. So it means for computable measure, we cannot define, in the set of computable measure, we cannot find the largest element. So now the next plan is to consider measures that can be approximated from below. So it means that there exists an algorithm that, given on X, prints a bunch of numbers. These numbers should be non-decreasing, and the limit should be the value of the measure. So the measure can always increase. And now this trick doesn't work. If we follow the smallest node, then it can later happen that suddenly this measure increases and the diagonalization fails. And moreover, there exists, so there is a new theorem that says, let me write it here. So there exists a lower semi-computable semi-measure, so they call it usually M, that is bigger up to constant factor than any other lower semi-computable semi-measure. So for every lower semi-computable semi-measure P, we have that P is smaller up to constant factor than M. So this is a theorem. So how do we prove it? Idea is that we can make a list uniformly approximable. So that means we can make a list that contains all our semi-computable semi-measure, and they're all uniformly approximated by a single program. And then our measure will be equal to M over X is equal to P1. So 2 to the power minus P1 plus 2 to the power of X, 2 to the power 2, P2 of X, and so on. So we take a mixture with positive converging coefficients. So that's how one can prove that such a measure exists. So here is
Excuse me, why does there exist a machine that remembers all the...
Yeah. So how does it work? It will just list all descriptions of Turing machines and then evaluate them, but also verify that they indeed compute a semi-measure.
It takes the infinite list as an input.
No, so it will make a list of all the programs, of all Turing machines or whatever. And then think that they compute a lower approximation of a semi-measure. And so it will check at each step whether the program is acting correctly. If it doesn't act correctly, the machine is frozen. And so here is a lower semi-computable semi-measure, and it's bigger than any other semi-computable measure, up to a constant factor. So now people can agree on algorithmic probability as measure P to make predictions. And one can look to conditional probability to assign probability. And this kind of solves all, this provides a solution for all questions you can dream of in foundations of probability. Okay, and so, so there are like Occam's razor. So there are nice theorems. For example, m of x is roughly equal to 2 to the minus Kolmogorov complexity of x. So that means that if a string has a short description, then description will play an important role in this prediction, such prediction strategies, and in the assignment of probabilities. So strings with short descriptions, they will be more likely according to this semi-measure. Okay, so strings with short description, they will have higher probability, and hence we will make fewer mistakes on them. So this is what people call Occam's razor. Okay, so now this is called continuous semi-measure. There is also discrete semi-measure. And so only Solomonoff for a very long time wrote about this. I think for 20, 30 years, this was, this is not true. Peter Getch also studied this. Okay, but there is discrete semi-measure, and this was carefully studied by Kolmogorov and Levin. And what is basically the same, everything I said is true for discrete semi-measure, just for the definition. Yeah, so here, the requirement is that the sum of P of x is smaller than 1. We can also speak about, so this is discrete semi-measure. Again, there is a discrete semi-measure that's largest up to a constant. This theorem is also true. For precisely that we take the same mixture and obtain this probability. And now we have a better result. Because for discrete semi-measure, like people use little m, we have that the logarithm of 1 over discrete semi-measure is equal to prefix-free variant of Kolmogorov complexity. I will say later what it is. Well, I think that we should, in 10 minutes, stop talking. So, okay. So, but now we can also define conditional complexity, conditional algorithmic probability. So here we have 2 inputs as string. We also have a condition as input, and we require that the sum over all x is at most 1 for every condition y. So this is conditional semi-measure. Again, we have an optimal semi-measure, and we have that m condition to y is equal to prefix Kolmogorov complexity. Okay, now let's go back to the goal of the talk. We wanted to find algorithmic probabilistic version of information distance. So we need to symmetrize conditional algorithmic probability. It's very easy. So we just require that px given y is equal to py given x. So then we will call it a symmetric conditional semi-measure. So again, there is optimal semi-measure. Again, the same reasons. We can build mixture over all such measure, put them in a sequence, and so on. Yes. And now we want to understand, so let us say that the universal, let us denote it with some special notation. So let us say that this measure is little m with 2 dots to discriminate from conditional algorithmic probability. And now we have a new theorem, and I think you will be able to guess what is this theorem. It's very similar to what we said about plane distance. So what might be the equality for this measure? It will be the minimum, oh sorry, it will be minimum of mx given y, comma my given x. Okay, and this is easy to prove. It's easy to understand directly from the definitions. So one inequality is really easy. So which one? And so we understand that it's smaller than mx given y up to constant factor. Why? Because in all our definitions we just added an extra condition of symmetry. So it is smaller than the minimum as well. And also by definition of universality, this is clear, the bigger than. So why? Now this is a very easy question. So what can we say about the minimum? This minimum satisfy all these conditions here. So minimum, when we sum over x, we know minimum is smaller than mxy. So when we sum over x, we get the sum condition just from the first term of the minimum. And it's symmetric by definition. And so here, algorithmic probability variant, we see this nice equality almost by definition. It's completely trivial. So before we had to work for plane distance. For algorithmic version, we get it for free. And now we go to the last step. So we have finished this one, but this is shortest part of the talk. So let us define, okay. I've already said what is coding theorem. So I will not give the proof, I promised in the abstract, but it was clear, it was too much. Okay, now last part, let us define prefix complexity and prefix information distance. Prefix Kolmogorov complexity is defined using special Turing machine. So halt, a set of halting programs should be prefix free. It means if one program halts, then the second, then a strict prefix of this program, the machine should always get stuck in a loop. So it's to deal with some cheating in a plain Turing machine, the Turing machine can scan the length of the program. After the program there is a blank, and you can use this length as extra input. And this creates some trouble when we relate to probability. And so to get this theorem, we need a special machine where programs are self-delimiting or are a prefix-free set. And then we can look okay, let's not speak too much about this. So let us just write down what is prefix-free Turing machine. So U is prefix-free. And now I consider U with two arguments as input and producing one output. So if for every string y, the set P for which U, P, Y halts is prefix-free. So this definition of prefix-free. And now we can define Kolmogorov complexity with prefix-free set. But just to remember, now machines are prefix-free, use letter K instead of C. It's a universal convention, especially when we drop the index of the machine. And so K, X given Y is again minimum, okay, just the same definition, U, P, Y equals X. And again, we can have optimal prefix-free machine to apply this definition. Now we can apply information distance as it was defined by Vitani and Lee in 1992 and also in 1998 in the more famous paper. So it's just the same definition of distance, but now with prefix-free machines. Okay, so now there is a big question. We have definition with prefix-free machines. Let's call it dxy. And we have definition with algorithmic probability. So is it true that this is again equal to logarithm 1m over xy plus O of 1? And so, well, first let us think again. We have expression for mxy. We said that it's equal to minimum of conditional complexity, mxy and myx. So this is equal by this coding theorem. By this theorem, it is equal to maximum. So we have, this is just for clarity, this is equal to maximum of conditional complexities, yx plus O of 1. So this is our question. Is information distance equal to the maximum of the two? Okay, so I will write the answer, but let us call this maximum E, because I will need it many times. And so there were 3 papers that say that this was indeed true between 2010 and 2016. But I've written a paper where I say it's not true. And but it's obvious that the 3 papers are false. There is no discussion. And prove that it's not true is quite complicated. And
Is everything published?
no. But I submitted in 2000, but it's together with, let me answer this in a minute. So let us have, however, I've proved that they are equal, except in very strange cases. So what I've proven is that this is a simple result. If x equals y, and E is at least a logarithm, so 1.01 log xy,
Is it the constant you used in the proof, or is it just a random constant?
no, it's of course.
It's important that it's not less.
Well, there is some formula in the proof, but I don't want to write this formula. Yeah. So then E is equal to D. Plus O of 1. So, yeah. So under these conditions, so there is positive result. But we do need these conditions. This condition is needed. Length x and y can be seriously weakened. So basically they have to have exponentially different length. But the precise statement is complicated. So let's not bother with it. So this is the new theorem 1. And the new theorem 2 is that for all n, there exist x and y of length n. So that the difference is double logarithmic. Such that dxy minus E of xy is bigger than omega log n. So this is second theorem. Okay. So now question, is it reviewed? So I wrote a paper during COVID when I was 4 months. So this result, it's 8 pages or something that's just game. Sasha Shen checked it, and most reviewers got through this proof. So, so I submitted it, but then after half a year I had to revise the paper. But then I never had time to revise because this result is extremely difficult. So coding strategy, bidirectional coding, it's like 20 pages. No, 10 pages, but there is extension for information diameter. It's even much harder. And so I didn't have time. So I wrote, so there was a long game with many strategies. And 3 times I wrote, this game is solved similar. And the reviewer saying, no, you have to write all the details. And so then it would be like a really long paper. I start to rewrite the paper, but it takes like 2 or 3 weeks. So I decided, okay, let's make general theorem that I don't have to say it's similar. But then I need to think about it. So I probably need 2 or 3 weeks without interruption. But this doesn't exist so far. So, yeah. So I will soon write a paper. I mean, revise the paper. But for information diameter, so all reviewers stopped when I said, do this in a similar way. They say, no. No choice. Okay, so it's end of the seminar. Yes. Yes.
Questions? Yes.
Suppose you have two strings of zeros and ones, x and y, of the length n.
Yeah.
And x is produced by a simple Turing machine.
Yeah.
And y is produced by a really random mechanism.
Yeah.
Lactose and coexist could be no simple algorithm for this. Is it possible to play formally that d of x and y greater than n minus constant log n?
What you say is...
Is this truth?
Yeah.
Statement.
So we just have to look to definition. Where is definition? Okay, let's use prefix. Oh, I lost my definition. So we need program that maps...
Okay, what is the theorem of the type? D, x, and y are deterministic sequence, random sequence, greater than n length of both, minus constant multiplied by log.
Yeah, you're fully right. So what to say the definition? So say definition, program that maps easy string to random string and random string to easy string. Now, random string to easy string is very easy way to do. We just have to remember the short Turing machine. But when we map to random string, we have to remember all bits literally. And so, by definition of randomness, only program that can do this will be length of the string. Yeah. And we even need more than length of the string when we use prefix distance. Because we need prefix-free program. And if we use identity mapping, it's defined so that mapping halts on all the strings. And all the set of all strings is not prefix-free. Okay. Yeah, sorry for long answer. Okay, it's end of the week. We should sleep or drink or whatever. Yeah. So
Question or no?
No.
Okay, let's end the speaker.